So Elliot's talk is on the study of the eclipses in 1810. So yes.
Yep. So as Renee said, I'm Elliot Paulson, and I've actually been working with Renee in the University of Manchester on the eclipses of Black Widow pulsar J1810 plus 1744, specifically looking at this at very low radio frequencies. So just a quick introduction to the actual eclipses, although we've probably seen quite a bit of this morning anyway. The radio eclipses are observed in many Black Widow systems. And in these eclipses, we see the pulsed radio emission diminished or fully eclipsed at certain orbital phases. And we usually see these to be dependent on the observing frequency at which we look at the eclipses, where usually at lower frequencies we see a nice wider eclipse. Often the eclipses are seen to be centered around companion inferior conjunction, so that's where the companion's passing closest to the line of sight between you and the pulsar. But what's really interesting is the duration of these eclipses imply that the medium or material causing the eclipse is actually spread much further than the Roche lobe of the companion, which suggests that the material really cannot be gravitationally bound to the companion star. And what I just want to highlight is that in-depth eclipse analyses have only been done for a very small handful of Black Widow systems. So just a bit about this pulsar itself. J1810 plus 1744 is a millisecond pulsar with a spin period about 1.66 milliseconds, so pretty similar to B957. It's got a fairly modest DM of around about 40. Its orbital period is really tight, so it's in about a 3.6 hour orbit, and the separation between the two bodies is just 1.33 solar radii, so it's in a really tight orbit. The data set that we've been looking at has primarily been from LOFAR, so we've had both imaging and beamform data, and that's using the HBAs, the high band antenna, so that's 110 to about 190 megahertz. We have orbital coverage of 2 full eclipses, 3 eclipse ingresses, and 5 eclipse egresses. And then to highlight some of the frequency dependency of the eclipse, we've got some Westerbork data. So that's at a higher frequency of 310 to 380 megahertz. So still low in the grand scheme of things. And we've got coverage of 1 full eclipse. So just to show the geometry of what we expect for this system, well, there were 2 papers a few years ago that basically settled on the inclination of this system being about 50 degrees. So if you look at the plot on the left-hand side, this basically shows a side-on view of the system. So looking at it from the orbital plane itself. Now the blue curve shows the Roche lobe of the companion, and this is of the companion and the pulsar, and this is all drawn to scale. And what we notice is the line of sight, should the orbit be at 50 degrees inclination, the line of sight passes really, really far above the companion Roche lobe. So it's really interesting how far away this material must be. Now looking at it from the top view, we see on the right-hand side here, again we see the Roche lobe in blue. This grey circle is kind of showing the orbit of the companion star. We're also drawing in it now. I don't know how well you can see this from the back, but the red dashed lines here are showing the higher frequency eclipse, so the 350 megahertz eclipse, and the green here is highlighting the orbital phases at which we see the lower frequency eclipse. And then just on the end of each of these eclipses, I've highlighted the orbital phases at which we see dispersion measure variations detected after the eclipse. So basically what I'm trying to show is whichever way you look at this system, the line of sight at which we see in eclipses is really far away from the Roche lobe of the companion. So 2 of the things we were trying to look at in this system is the dispersion measure and the scattering around eclipse. So to make a measurement of these, what we actually did is create some 2D templates. So that's looking at with the frequency and pulse phase resolution of the data set. Now, if you look on the left-hand side, this is basically one of the templates made from the out-of-eclipse observations, so far away from any dispersion measure changes. And you basically see the pulse, as you expect, is much brighter at the lower frequencies than it is at higher, and it's nice and wider at the bottom. And as you go to higher frequencies, it's getting thinner. Then what we did from that stock out-of-eclipse template, we then made a full array of templates where each one has an extra bit of dispersion and an extra bit of scattering applied to it. So just an example of 2 of these. We've got one in the middle here, which shows a template where it's been dispersed with an extra dispersion measure of about 5 times 10 to the minus 3 per centimeter cubes. And one on the right-hand side is showing one that's been slightly dispersed, but also slightly scattered, with a scattering timescale of about 20% of the spin period of the pulsar. Now with this full array of templates, what we did is we took each time interval of data, and then we applied every single one of the array of templates to each data set. And from that, from your least squares fit, you basically get a chi-squared value of the best fit of that template. So then you end up with essentially a big map, big chi-squared map for each time interval of data, where you can look for the lowest chi-squared, which will highlight the best fitting template to that data set. Annie?
Can you fill me in? What is the color code representing?
Sorry.
What's plotted on these?
So this is basically just showing the pulse, essentially, of the pulsar. So this is pulse phase, and then this is the frequency. So if it's easy if you just look at this one, really. So
it's pulse intensity, is it? Yeah.
Pulse intensity, yeah, sorry, yeah. So it's like brighter at the lower frequencies and then fades out the higher in frequency you go, because it's got quite a steep spectrum.
Is that characteristic of your low-power band? That's how different it is from 110 to 180?
Yep, this is literally made up of essentially just high signal to noise, taking all of the out of eclipse observations and just stacking them.
So these observations, no, these are not observations?
These are made from observations, and I've just smoothed it to get rid of like the small amounts of noise, which is why it doesn't look like there's any noise. What's that, sorry?
Is this corrected for the bandpass of Loafer or not?
Yes, this has been all calibrated beforehand.
Yeah, but not bandpass corrected, right? So the bandpass drops at the edge. Did you?
Yes, but doesn't that get removed in the Vlad's calibration code? Should remove the. Oh, does it not?
But you're working relative to each other, so at that level it doesn't matter at all.
Yeah.
Although the bandpass is double peaked, and I don't see the second peak in there, so that's why I'm asking.
All right.
I forgot the details. We could
Well, we can come back to that later. But either way, this is made up of the data, and then it's been fit to the data. So either way, the bandpass or no bandpass should agree between the template and data set.
Is it like this when it's in Janskis or something? Millijanskis, the color scale?
Yeah, it should just be linear with flux. Yeah, it's not in actual units of.
That's all right, but it's linear in flux.
Yeah, it's linear. Yeah.
Actually, the bandpass is we divided by the bandpass, otherwise the off pulse would be showing some.
Yep, so anyway, this is just showing some results from that fit. So this is showing one eclipse egress. So you can see the orbital phase, you probably can't see it there, but it's about 0.31 to 0.4, so it's just after the eclipse. The top panel here is showing the normalized flux of the pulsar. The middle panel is showing the delta dispersion measure, so that's the measured dispersion measure on top of what we see out of eclipse. And then the bottom is showing the delta scattering timescale, so the extra scattering that we see on top of that out of eclipse. So what we see in the flux, for example, initially it's at 0 when it's in eclipse, and then you see a nice clean rise out to its out of eclipse level, and then it levels off nice and flat. You see the opposite effect in the dispersion measure, where initially out of eclipse it's at a value above about 4 times 10 to the minus 3 parsecs per centimetre cubed, and then that falls off about the same rate at which the flux rises to its out of eclipse level. And also we detect a very small amount of scattering after eclipse, which closely goes down to its out of eclipse level. These, like these, do you mean like this one, for example, or these? Yeah, this, I'd probably take it with a pinch of salt, because sometimes as you get in here, as the flux gets lower, sometimes you start to get random fits.
No, because you have like there, basically, right? These.
Well, and then higher up, you get the point way up, yeah.
Yes.
Yeah. So I mean, when the flux starts getting low, occasionally you get like a random. It just comes out of the fit. So I wouldn't take these far ones too seriously. Usually, whenever these are.
There might be another point that is just slightly worse, but would be consistent with the rest of the.
Yeah.
I mean, if you're really in a low signal to noise regimes, it's.
Yeah. Often when there are weird ones like that, I've actually looked at the data set myself, and I'd probably discount most of these as being like actual sharp rises. Yeah. And then these are just from like where data's been deleted for RFI, so it's just kind of left a big gap. So if we move on now, this is just 2 more eclipse egresses. So if we look at this one on the left-hand side first, it's showing a fairly similar rise in flux to the out of eclipse level. There's kind of a spike here, which is interesting in flux. But this time the dispersion measure has got a much longer and smoother decay back to its out of eclipse level. And again, the scattering is just slightly above the out of eclipse level. And then on the right hand side, we see something really interesting, where both the flux and the dispersion measure are now, you see these like real clear features. And from this, we can kind of infer that the material is quite variable and possibly quite clumpy as well. So yeah, that's basically just saying that from these eclipse egresses and all the other data we've got, it's suggesting that it's quite a dynamic medium, and there is a detectable amount of scattering after eclipse, but it doesn't seem anywhere near enough to fully scatter out the pulses beyond detection.
How far separated are these eclipses? Is this 3 hours later?
So this one is like kind of a month separated from these two, but these two are on consecutive days, so about
Okay, so 10 orbits later.
yeah, pretty much, yeah. We do actually have some more interesting ones which are consecutive orbits. Yeah, but I'm not showing here, but you basically do see big variations.
They do change from what they
Yeah, yeah,
completely random.
a lot, yeah. So now just moving on to the imaging. This is just a quick slide showing that I basically calibrated the imaging data with standard LOFAR software, and I made images with CITA on 1 minute time intervals. Now this one on the left basically shows an example image out of eclipse, so you can see the pulsar flux in the middle of this red circle, and then in the middle of the eclipse, you're basically not detecting any flux from the pulsar above the noise level. And then at the bottom here just shows the light curve that we've extracted from these images. So you see there's about 1.5 eclipses here, and these are consecutive eclipses because it's just a continuous run. So initially you're in eclipse, and then you're at the out of eclipse level here, then you catch a nice eclipse at the end. So putting all this together, there's two plots that I'm showing here, and this is kind of zoomed into the eclipse orbital phases. The one on the left is showing the delta dispersion measure, so the extra dispersion measure on top of that out of eclipse. On the right, we show the flux variations around the same orbital phases. So you see on both plots is these dashed vertical lines, and this is an orbital phase of 0.25. So that's basically where the companion is closest to the line of sight between you and the pulsar. And what we notice in both of the plots is that there's a clear asymmetry. So there's two things I mean about that. First of all, you see a clear asymmetry in the dispersion measure, so the amount of material you're detecting before and after the eclipse. But also, you're seeing that in both plots, the whole eclipse is shifted significantly after a phase of 0.25. And also, if you look back at the dispersion measure plot now, this red curve is showing the higher frequency data, while the grey points are showing the LOFAR data.
Is the higher frequency data just one across the
Just a single eclipse, yeah.
So it's very variable, that additional one.
Yeah, yeah, yeah. We see that the higher frequency data is probing further into the eclipse, and the column density is continuing to rise. Now on the right-hand side, in the flux plot, we've got the same colour scale, so the red is showing the higher frequency data, probing further into the eclipse. The grey points are showing the LOFAR beamform data, but now we've also got this blue curve, which is showing the flux from the imaging data that I showed on the previous slide. And what we see here is that the flux from the imaging data and the beamform data are dropping into eclipse and recovering from eclipse at pretty much the exact same orbital phases, which really is suggesting that the flux has been removed from the line of sight, as opposed to like dispersion smearing, for example, which would just smear out pulses beyond detection. Still expect to receive flux from the pulsar in the imaging. Yep, so one more thing I just wanted to talk about is the duration of the eclipses. Basically, to make this plot, I split the LOFAR band up into 4 separate subbands, and then the Westport band up into 3 separate subbands. And then for each of those subbands, and essentially the duration by eclipse. So this is showing a log of the eclipse duration against the observing frequency, and you see that it's really well modelled by a power law with an exponent of 0.3, which is interesting because it's actually consistent with that found for J22 that pulsar, and also B57, which you've heard a lot about this morning. However, we kind of want to look a bit more into this, because from the previous slide, we're showing quite a lot. So we thought, instead of looking at the eclipse duration as a whole, we kind of split it up into the duration of and the duration of the durations plotted at the top here are to be well modelled by a power law. However, if we look at the ingress durations at the bottom, this LOFAR band seems quite interesting, where it seems to be following a much flatter relationship with frequency than you'd expect from a power law if it's the full data set. So it's kind of suggesting that there's a bit more of a complex relationship going on in the eclipse ingress. Sorry.
The green points are Westerbork.
Yep, these are both Westerbork.
You're being very conservative in your error bars.
Yeah, I've been conservative there so far, yeah. Yeah, especially because you can see, like, here they are, really are flat. Yeah.
Sorry,
That's,
can you just repeat your last statement about the ingress versus egress?
yep, so we're basically saying that the egress durations seem to be pretty well modelled by a single power law between the whole frequency range. However, when you look at the ingress ones, I don't know how clear it is back there, but basically these points from these three separate ingresses there, and they all seem to follow in quite a flat relationship, something like the rule is kind of like a best fit, which seems very different to the full band up to 400 megahertz, where you see like a real drop in the Westbrook data. So it basically seems to be following different relationships across that frequency band.
And you can see it. Can you get back to that slide where you have like the yeah, there. And here it's well, okay. We don't quite see the multi-frequency LOFAR data, but like here, I mean, you can tell they're all like stacked together, the LOFAR data, and then you have like this huge gap to WSRT. And here you still have the gap basically in the LOFAR data. Then you do have well, I think it's in the paper. You do see like a clear, like change for the LOFAR bands, but on that side, like there's no change, and then like that gap.
Yeah.
So it's completely.
Strange.
Yeah.
In ingress also, there's almost no additional PM in the low part band.
Yeah, there's really
You just something hit a wall.
there's really nothing. Yeah. It's very interesting that.
Well, but you hit the wall at the low frequency, the effect just
Oh, yeah,
disappears.
yes. I mean, that's
Yeah.
obviously what's happening, but still.
Yeah, so just to summarize before we start discussing it all, we basically see that there's a very variable eclipse medium or material. We don't really see any steep scattering trends suggestive of it actually being a cause of the eclipse. We see that the continuum eclipse is equal to the pulsed eclipse, like really suggesting it could be something more like absorption. We see a clear frequency dependence, but there could be a bit more. There could be a bit more to look into this, splitting up into ingress and egress. We see there's definite asymmetry in both the dispersion measure and the actual position of the eclipse. And we have seen this before in other systems, and it's usually attributed to a bit like was drawn this morning, the kind of eclipse medium is just swept back due to orbital motion. So after the eclipse, you're still intersecting material for quite a while. And yeah, just the last point is that there's a paper in preparation with a heck of a lot more information than I've just been able to talk about. Yeah, that's it.
Does this also have rotation measure or features it?
I've spent a long time searching for rotation measures, and I've just not found any polarization at all in any of the observations.
And there's not even induced polarization during the eclipse.
I've also looked at short time intervals. Just can't find anything there.
So with your delta DM, what do you get for the electron density if you assume some reasonable capacities?
Yeah, so it's again about similar order to the B1957, so it's about 10 to the minus 4 centimeter per centimeter cubed. 10 to the 4. It's about the same as 1957. I can't remember off the top of my head.
But
Yeah.
that's DM units, right? So then, in terms of any, so sorry, got the paper here. That is right. Is that your number?
Yeah, so 1.4 times 10 to the 5 per centimeter cubed.
Per centimeter cube. But you want to know column per centimeter square?
Centimeter cube, yeah.
Per centimeter.
Yeah, that's
cube.
that.
Yeah.
1.4 times 10 to the 5. Yeah.
What's the equipotential magnetic field that we just in the pulsar wind energy?
It's around about 20, I think. It's also in here. It's fairly similar to 1957.
Gauss.
Yeah, Gauss, yeah.
So then if you put in 10 to the 5 of n, it gives you a large T, isn't it?
Yeah.
Yep, I've
Very easy to pick these up.
gone through it all in the paper, yeah.
You know, what this is, you see this persistent pattern now in the asymmetry of eclipses. The only way I can see get this to work is because the problem is that you take the density, as we were just discussing, and multiply it by a reasonable speed that would give you a reasonable Coriolis deflection. Right?
Yeah.
And the pressure is tiny compared to the pressure of the pulsar wind. So how does one reconcile this? And the only way I can think is that this is indirect evidence for a magnetosphere, where the magnetosphere is much more substantial, it may have a much higher plasma column in it, but it's away from the line of sight, out of the line of sight, but it's providing continuous seeding of electrons into the wind through some sort of reconnection, Dungy type reconnection or
Yeah, yeah.
And so you're not necessarily seeing a continuous flow, but rather there may be some off-axis sourcing that's, I don't understand the dynamics.
Yeah, yeah.
Otherwise.
And how would it be on the head side of it?
Well, I mean, you would need to have enough plasma density in the magnetotail, for example, magnetosphere for that effect going on. If it's just pure magnetic field, of course, it's a relativistic thing. It just will be swept back by the relativistic pulsar wind.
Yeah. Yeah, maybe we should move on to the next talk and then get back to it. The discussion.
Help with the next code.
Oh, right. Okay. All right. Well, thanks, Elliot, again.
Yeah, thanks.
Good stuff. So about the ATC survey and pulsar connection.
Yeah, and I work for Menlo Astrophysics, and there is a big team behind it, led by Keith Bannister. First of all, what Menlo Astrophysics is, and just to make you all envy, it's not because we are very manly, but because we are based in the suburb of Sydney called Manly. We are just next to the beach, and we are in a very nice area next to the ferry, and what's more, just here behind that door is a brewery. It's very nice. It's called 4 Pines, and yeah, I think all the Australians would know what that is.
They were just sold to InBev.
Well, it's actually expanding, so if we wait long enough, it might actually get right to our building. Anyway, so it's effectively a Mark Walker Institute, and I'm very lucky to be working with him if I'm doing scintillometry, if I do any scintillations. Right. I think Matthew has explained most of that. He actually showed the very same data today. And the ATISI survey for galactic plasma lenses, ATISI is standing for Australia Telescope, more widely known as the compact array at Narrabri, survey for extreme scattering events. And these are variations in the brightness of extragalactic sources caused by galactic plasma lenses, which are large, apparently coherent structures. And they are interesting because they don't quite fit into the picture of the ISM that we have. At least we have many doubts that they do. And they used to be hard to spot. And again, Matthew explained why. But recently, Keith Bannister had that beautiful idea that because of the strong frequency dependence of plasma lensing, you can just, rather than looking at like a handful of quasars every week for a number of years, you could just be looking at 1,000 of them for just a minute, once a month. And you know, they all have this boring power law spectra. And when the plasma lens hits, you have something like that. And it quickly evolves through the spectrum. And you know that it's time to start your follow-up. So the idea was to do that follow-up in real time. And we did that. And we had some optical, X-ray, you name it, VLBI data on all this stuff. And the highlight so far was that first real-time detected extreme scattering bands. And we devised a way to turn the dynamic spectra into the estimates, basically, of the electron density. And we were able to rule out my favorite model of ESCs, that was Pennant-King model. And I think that was the most beautiful with the underdense lens. But I think what Whaley Penn does, if someone rules out a model of his, he just proposes an even more beautiful model. And yeah, so. Another highlight, which is not very widely known, was that source PMN 1106 which just shows the craziest radio spectra that you've ever seen. That's just a selection of them. And in particular, this one with a kind of kinkiness, we believe was caused by a caustic crossing in the dynamic spectrum. And for that explanation to work, and we don't have any other explanation, but for that explanation to work, the source has to be optically thick. It has to have a sharp boundary, and that sharp boundary has to be concave. And I'm not going to speculate what that is, but you're looking at something that is crescent shape and right in the middle of an active galactic nucleus. And finally, the most interesting thing that I'll be talking about is that source PKS 1325, 1322, which has led us to that hot star paper. Right. So that's kind of the most extreme intraday variable that is known. These are hours. So it's over 8 hours. That's what happens to its spectrum in real time. Hmm?
That's like real data going.
Yeah, that's real data. That's the same as in the form of the dynamic spectrum. And it's probably not the most extreme of them, actually. Yeah, that's what they do. Some few other of those light curves in different bands and the corresponding dynamic spectra are here. And we believe that an intraday variable is caused by a nearby screen, so that the pattern that is projected hasn't had much time to diverge. So it's small, and as we move through it, the things change quickly. Now, naturally, we wanted to do a follow-up. And if you just load that source up in Aladdin, what you see is that huge spot there, and that is Spica. And Spica, it's just less than 9 arc minutes away. It's the closest B star we have to Earth. It's, by the way, 16th brightest star on the sky, and it's just 0.2% from the line of sight to that quasar. Basically, there are only like 4 IDVs so extreme known, and so they are extremely rare objects. And we find them near another quite rare object. So is that a coincidence or not?
So the circle there is not the size of Spica, is it?
I hope so. So that's 9 arc minutes here. So that is the PKS, and that's Spica. So the question, yeah, because whether that's a coincidence or not. And the clues that we have to answer that question come from 3 other, well, actually 2 other known extreme IDVs. They are 0405, 1819, and 1257. This guy has stopped scintillating in the year it was found, so we didn't have a chance to get an annual cycle for it. For 1819 and 1257, the annual cycles are well known. The annual cycles come about from that small size of the pattern and relatively slow motion that we find here. On top of that motion and those scales, the motion of the Earth matters. So sometimes you move with the pattern and the changes become slower. Sometimes you move against the pattern and they become quicker. And if you just plot that up as a function of the day of year, or just the day, the MJD, you find those nice dependencies. And turns out they are well fit by just a one-dimensional model where the magnification only depends on your position in one particular direction. And from that you can figure out all the kinematics, like the size of the characteristic size of those scintillas as projected onto the Earth orbit, the velocity of your screen, and so on and so forth. And it was long known that J1819 is close to Vega, but it was basically everyone's knowledge, but I'm not sure that there was much value given to that. Now, turns out that for Beck's 1257, there is a hot star nearby to it, and it's called, because they are all these screens are close to us, so all these hot stars have names. They are bright. This one is Al-Hakim, or Iota Centauri. And from the annual cycles, you can figure out the orientation of those screens, of the major axis of that screen. And turns out in both cases, they point towards those hot stars that we now think are somehow connected with these variations, with the phenomenon of extreme IDV. You can work out, of course we can just compare the predicted and actual values here and work out the probabilities that these come about by chance, and the probabilities are quite low. But yeah, that's basically, you populate these things with your hot stars. You know our local density of hot stars. We know how they move around, and so on and so forth. And both individually and taken together, these numbers are low. But what excited me most is that in the case of Spica, we have a prediction for the annual cycle which has no free parameters except for the Averill scale. And that Averill scale was fed back in July when I gave a talk at Canberra, and JP was there. Stefan might be, well. So, well, and now we have the data for it, and you see it lands pretty much where predicted, and it's just a single free parameters there. So that kind of makes me believe there is something about this connection. So what are these structures? What we know? They are seen about a parsecs away from hot stars. The sizes that are inferred from the statistics of the IDVs are about 100 AU, well, plus or minus an order of magnitude. From the rate at which you find those things, you know that there should be about 100,000 of them per star. They are readily elongated, and of course they are ionized. And there are things that are very similar. They are found in the planetary nebula, and they're called cometary knots. Again, there is a very hot star, but it's small and dim, therefore you can actually see those. If you put those cometary knots next to Spica, you wouldn't see anything, just because it would blind you out. And we know that they have photoionized skins. And for these objects, we have a bit more knowledge. We know that besides the behind those photoionized skins, there are dense molecular cloudlets. They are about Earth mass sized, and they are assumed to form late in the life of the star. Now, if these things are indeed the same, then of course that cannot be true for our objects which cause the IDVs, because we see them near hot stars which have formed quite a while ago and have survived so far. So we really don't know what they are, how they form, how they survive, say the irradiation is not a problem because they are so dense that they are very strongly self-shielding. They have enormous survival times. Could they be self-gravitating? And if they are, what the total mass? Has there some implications for the dark baryons problems, or perhaps the dark matter itself? That is not really known. But that object did impress us so much that we have actually now changed and killed off the ITZ project and started the AT IDV. And so what we did, we just selected all our objects which were behind the Hill spheres of close hot stars. They are shown in those objects that are in the new sample are shown in red and orange on this plot. And you would know what that Hill sphere is, because that's Sirius. That's probably bigger. And we had just we had just first observation, and I think we have 15, as Jamie Stevens put it, mildly convincing candidates, but I think at least 5 of them are varying strongly by 50% in that sample on the first observation. So we just took a few hours spaced exposures here. So the rate did indeed go up. That's a very good indication. And I'm not sure if I have much time left, but I just thought that given that there is something about those alignments, I do strongly believe there is. And at the same time, we've seen how the sheet idea works well for pretty much everything. So I'm wondering whether there is any way to basically combine them. And to this end, I just want to emphasize that the direction that matters in the case of IDVs is this direction. When you move along that line, nothing changes in your brightness, basically. It is those things, those motions then that change your brightness for the IDV. So could that be like a sheet somehow warped around the direction to your star? Could that be related to streaming? Could that be related to there being a shadow cast by something which prevents prevents the gas inside that shadow to be ionized? I don't know. Yeah, that's it.
Yeah, okay. Okay, so by the way, it's the coding time, so if you want to see it, you can disappear shamelessly. Otherwise, yeah, we'll take some questions. Jason?
So trying to reconcile two statements. You said that its chance alignment is very rare, but then you were able to pick a sample with looked like a large fraction of objects that are right next to A stars. So how do I reconcile those two things? It looked like from your sample that you chose for things that are near hot stars that there's a lot of them that are near hot stars.
Yeah,
so
there is.
Chance alignment probability 10 to the minus 4 if you have a sample of a huge number of objects.
I think it's more like 10 to the minus 3, and it's in the full sample that we had before. That number comes from massive survey, which didn't have that selection restriction to being behind the Hill sphere of a hot nearby star.
Maybe I misunderstood the slide. It just looked like you picked a lot of the
that's
order
right.
unity of the possible targets were.
If you get back to the other side.
You mean this one?
There, right?
So among those red and yellow or orange, I'm not sure how many. It's probably like 500 of them.
So I didn't really understand properly that plot. Can you explain what so these are all, what the colors are and the
Sorry. Yeah. So all these points used to be in our sample.
Okay.
Then we changed that I should have said that, yeah. Then we changed that sample to go for a more northerly sample, so that these dark blue spots, just to have reliable VLBI on them, because we are in Australia. Like, and for the new project, we only selected those that lie behind the hill spheres of nearby stars. Hill spheres. The hill sphere.
The radius where you're dominating the gravity over what?
Yes, the hill sphere is selected to make sure that these structures move with the star.
Okay. So
Yeah.
it's relative to the galactic
Yeah.
tidal field or nearest neighbor?
Relative to the galactic field, of course.
Where are Magellanic clouds?
The Magellanic clouds, I think they should be around here.
And no candidate hot star. Magellanic cloud and
Well, but they restricted
Yeah,
to nearby hot stars.
So I think the two factors are probably just, this is 30 parsec compared to 1 parsec before, and that Matthew's pointing out that the annual variation gives you a cone, not a circle, but rather a direction. So I think those two factors probably come in.
So for Vega, the sphere is very big because it's just
Well,
very close to us.
This one is Sirius.
Sirius.
Yeah. I'm sorry. Yeah. Normally we would see that plot the other way around because it's the galactic light is going on to that.
Matthew.
Is it possible to do a Hubble observation with the Leo stuff or something speed that?
If you give us time. Yeah. But we did get time on ALMA, so we should have an answer in H2 and CO this semester.
Yeah, that would be, that's probably
Yeah.
better. I was going to ask a related question.
H alpha maps are there, but they are probably too close at the moment at the positions that we have. So if anyone has like data.
Yeah,
We do
there's
have
not-
data. We do have data towards J1819.
Yes.
In fact, we have spectropolarimetric imaging as well from low pass. And there is an indication that J1819 sits on the edge of some rotation-ish cloud.
But the problem is that that cloud is much closer to us than bigger. Yeah. So I'm not sure how to reconcile that.
The other issue is that some of the scintillation modelling puts the scattering screen towards J1819 considerably closer than Vega as well. It's a question of whether you believe or what you believe.
I'm still unclear on the different categories. What are the different colors? What are the blue ones?
The blue ones are those that didn't make it to the new sample.
So these are AGMs that you're not observing?
Yes. Not anymore. We used to have them.
What are the circles?
The circles are the hills, the projection of the hill spheres onto the sky.
Stars within 30 parsecs.
Away from us, yeah.
So I guess, well, I'll just use my privilege as chair to ask a question. So presumably you might see, well, not quite, because I guess the structures might be different from one source to another, but if some are nearby, would you expect maybe to see some sort of like correlation over time of like the IDV?
Basically what we want is to find a few of them near one single star nearby and see where they all point in the same direction. That would be the ideal case.
Now, in order to get order 1 flux variations, you need strong lensing, which normally means you would have multiple image formations, you would think. Now, in Bannister, he talks about VLBI not actually resolving anything. On the other hand, that bound isn't particularly profound, since you don't really expect it to be resolved. In last year, also tried to look at ESE, 20 years ago. He may have seen an extent, but again, he couldn't tell whether there are two sources that form. So it looks like we're kind
We do have VLBI measurements. We do see them moving around for another source. We've got another ESC 1740, which I haven't shown because the guy who is responsible for VLBI is not writing up the paper. JP, don't tell him about that. Yeah, that. Yeah, he's supposed to be writing a paper, but he's not doing. But there, we don't see multiple imaging, but we do see how the image dances around in a way that is consistent with the very simple theory of how it gets magnified. I don't know.
Not resolution. I would have thought it's not resolution. I mean, my reading of the literature there is that. I mean, so the question really is it wide? Are any of them wide enough that you ask one could see them at all?
I don't know. I can't say that.
Because then you just nail, I mean, it's kind of marginal. Most of these expected separations are kind of
I think, to be honest, they're waiting for a better event. I think the 1740 observations, if that's the data set I remember correctly, which I've never seen, by the way, but I've certainly heard about, is that it was pretty hairy because it was low towards the horizon. And so
No, that was 1106.
Oh, was it? Okay. Well,
And the first one was low as well. That's what led us to restrict to those northern sources.
I think it's just a question of getting the right example where there's enough signal to noise and so the Artesi, they've changed, well before they became AMIDV, we've changed it so that you were concentrating on more northerly targets for which you could get the VLBI.
Yeah, that's here they are.
Just be patient.
So how many are you observing now? What's the list?
It's about, I think, 500 to 600.
500 to 600?
Yeah.
And they're observed once a week, did you say?
No, they are observed once a month for a few hours in blocks of 2 or 3 days. Like, I think 8 hours on 2 or 3 consecutive days.
That's 2 or 3 consecutive days.
Yeah, that's just to see those changing on the intraday scales, intra-hour scales. Yeah.
So have you actually checked to see whether none of the other massive sources, those 500 or 600 sources, were near suitable stars?
Well, massive sources don't have to be like nearby.
Well, I mean, the thing is that you already have a ready sample of multi-epoch observations of IDVs across the sky. I'd be rather surprised if none of those lines of sight went near A stars or what have you, say with 100 parsecs.
We want to have annual cycles to say something about them.
Yeah,
with massive, we don't
get a very good indication of I mean, you can do a rudimentary test on the sample just by looking at, you can tell the things that have nearby screens because it's easier for the sources to meet the source size criterion, right? So Barney modelled the massive sample in terms of you could reproduce the statistical properties quite well with this sort of homogeneous IGN with a distance of about a kiloparsec, I think it was. Yeah. What did I say? Anyway. And the question is, which ones of those stick out like sore thumbs? And because there are some fast IDVs in that massive sample. And the question is there any correlation with anything else along the line of sight? I mean,
you need to take the data from the massive survey and select out the rapid variables and ask what were they show.
Or perform the inverse test and say, well, these are where all the A stars is within the radius of 100 parsecs. Do any of these lines of sight go anywhere near these IDVs?
Well, that was. Well, that was obviously the first thought that Haley Bignell had, because she was involved there, right? And for some reason, I'm sorry, I probably cannot tell why because I don't know, but she decided that it wasn't quite the right way to go.
Well, I need to have words with it then.
Yeah.
When I get back to Perth.
Yeah.
Yeah. Because I think they are good enough to tell you whether you do have some sort of annual cycle, because we got pretty good light curves over 3 or 4 days for what was it, in the end, 5 epochs. 4 epochs over 1 year. It's not as if you can't say anything already.
Maybe one last question, and then, well, anyway, that's kind of like at the end, so we can just have more informal discussions after that. And
maybe this is already informal, but
yeah.
there was a paper just a few weeks ago by Vedantam and Reedhead, where they used the Owens Valley short-term variability sample. And again, they seem to have a different vantage point, that they thought that plasma lensing is perfectly understood, and therefore they claim to have detected mini lensing by intermediate mass black holes, because they said that they could rule out all plasma effects because they understand them so well. Is that a consensus opinion, or is that just something that you're thinking?
I got one thing this week, is that we completely understand plasma physics of lensing.
That was based on the strong achromaticity and the very high frequency at which they observed this thing, right? This was at many tens of gigahertz.
It went all the way to 10 gigahertz. They covered a very broad range.
So the argument that they have against plasma lensing is that it was perfectly achromatic.
Yeah. What?
Isn't it true if you have a 2D lens in a way that you can pretty much do anything?
Well, with 2D lens, you can model any given dynamic spectrum that you have, right? Because you can lens in one direction and then disperse them in a different direction. Yeah.
The problem is that if you're seeing this at 100 gigahertz, it's some incredible length. And then I suppose the Vedantam et al. Argument would be, well, which is the crazier explanation? An intermediate mass black hole or some incredible plasma lens?
Well, incredible meaning they had a sample of that. I couldn't quite tell how many objects they're actually monitoring, right? They're monitoring hundreds of objects, that must seem to me my inference. And then they find something funny going on in one of the events. Okay, so now you've got, one in, I don't know how many, it's not quite clear how to quantify how many objects you observe for how long, and you find something, and yeah, is it funny or not? It's a bit of a...
I haven't dug into this paper at all, so I don't have an opinion.
Well, I must admit I had to read it quite closely.
Okay.
And I would say it's an interesting idea that needs to be out in the literature and debated, because the interpretation of the data is, well, it's clearly something very interesting, but I don't think the intermediate mass black hole explanation is but one explanation, and there are many.
Including plasma explanations.
Well, not necessarily plasma. You can have bound electrons, molecules, whatever. I mean, something that has those clouds, they are ionized on the outside, but they